to, because Deirdre couldn't log on earlier, so we put Chris in earlier. Sorry, everyone. Our timetable is a bit fluid.
I've got a 3:30 till 4:30, but I'm very flexible. I can do before or after that.
Thomas, you go now and I'll go after you.
So after Thomas, I think we're going to have the early career researchers, and then, yeah, is that cool? Okay, sorry everyone. So Thomas House is based at Manchester, and he's been doing some work with ONS on looking at household models. So I believe that's what he's going to talk to us about today, and I will pass over to you, Thomas.
That's great. Can everyone see the slides? They're okay.
Yeah, perfect.
And hear me all right. So, okay, so I'm just going to talk quickly about the ONS studies. The UK government, lots of people are not convinced, has done terribly. Lots of criticism, lots of praise, but one of the things that is often singled out for praise is these two very large community surveillance studies. And although it's only ever at best approximate, they are based on the attempt to give an approximate uniform random sampling from the population. So the REACT study is a cross-sectional design, so taking it has waves, and in each wave they try and get lots of people, but that's like definitely one individual from each household, no intention to sample people repeatedly. Whereas the ONS study, ONS-CIS, has this more complex household-based longitudinal design. And one of the key aims of JUNIPER was to help provide modelling and statistical support for that study. An example of that would be, Kira on the first day talked about the mathematical writing support that we have. Obviously, that didn't get into the kind of, politics of the controversy around the incidence calculation, but just having a kind of constructive explanation of here's what the ONS-CIS is doing with its incidence calculation that you can point people to and just go, here's an explanation for the kind of intelligent general numerate reader is so useful. And so I'm going to talk about one of the more technical things, but this incidence calculation is also being held and developed by the Cambridge Biostat unit group within the JUNIPER consortium, are kind of developing this. They're developing this incidence methodology that's detailed here, and hopefully at some point we'll get a kind of household explainer, but it's a bit more fiddly. So the ONS-CIS has this regular reporting role here, which, so it publicly releases every week up-to-date information from the study, this is a kind of schematic of what is tricky about this household longitudinal design. That so as you got 4 participants, that's the PIDs, participant ID 1, 2, 3, 4, and we follow them over weeks. And at the start of the study, they're followed approximately weekly, but of course it's the real world, so people won't be picked up, there won't be exactly a week between them. And then people are followed up monthly, and you could have an epidemic that was spreading through the household like this red tree that you might, if you were contact tracing, you'd try and really follow the events in the tree. But what we're doing is coming through, at a certain time and capturing everyone in the household. So the same things that make it an unbiased estimate of prevalence make it hard to follow transmission through the household, although that is something that as I'm going to show, can be done. Just a bit of history. Household models are, whenever people start with the epidemic model, they'll write down these nonlinear ODEs for the SIR model. But household models have been around about as long. And although there's still this sort of SIR type framework, you need to account for randomness in them, right? And the importance of households in infection stems from the fact there's this close repeated nature of contact within the household, meaning that within household transmission of infection is common. Most people live in these small stable households, so they're natural unit for data collection. Interventions are often designed at the household level. So whole households, this pandemic, have tended to be isolated. School LFD testing, has an impact on the household and so on, right? So what we tend to say to people, what we often say to people is, you stay with your household members. We didn't split households up. like some countries did. And just again, a bit more history. I would say there've been kind of 3 eras of household studying. About 100 years ago, Reed and Frost's unpublished work was done on the first stochastic epidemic model. I've since found out from George Davies Smith there's a really interesting history actually of people, of these early infectious epidemiologists and stuff they did, so I should probably update this slide on the basis of what George found out, but not that there's anything wrong here. It's just a really interesting. There's really interesting extra stuff to the story. And so they tried to simulate this stochastic method using a kind of the Monte Carlo methods available at the time, which was a roulette table. Then you've got Bailey and his book on how to analyze these using what probabilists call spectral methodology. So this approach to stochastic processes that we sort of teach and learn now was actually developed somewhat to study these household models. And then later you'd get Hope Simpson's experiments on transmission of measles and so on. Then later in the 20th century, you've got, so Hope Simpson was relying on symptoms, right? Doing measles, mumps, and rubella, are you spotty or not, right? Then later in the 20th century, Frank Bull derived this final size formula that was more general than Bailey's. And people like Cheryl Addy, Ira Longini, Betts Halloran all did statistical work on this, and things like the Tecumseh flu study. So Tecumseh was based on viral culture. I think they tried to grow the virus in pig's blood to determine if you had flu. So it was culture. And then the modern approach, 21st century, tends to involve MCMC. And on the empirical end, obviously things like PCR and modern molecular techniques really change our ability to detect things. We're not reliant on culture. As is often the case, though, in an emergency, we use the last era's mathematical methods, and that's what I'm doing. So I'm using a generalization of the Addy approach because that in an emergency, we don't have time to get, don't have compute time or coder time to get MCMC running, although I hope with the kind of things that Chris is discussing getting more ubiquitous, that those will get routinized sort of thing. So our paper's now peer-reviewed through peer review. The archive version is the one that's going to be published in the journal. It's based on this previous preprint with Timken Yanjui, and what we do is apply these balls or sort of Addy type final size equations, and we justify their use by splitting the data into time periods. There's some code available applied to open data on GitHub. And I'd say this is reasonably principled, but there'd be, ideally we'd have done a big MCMC. Simon Koshber's asked me at Epidemics, what's the future for huge data like this? And I think it would be lovely to do huge MCMC for it. But that is, hopefully we'll get JUNIPER 2 and be able to do that, or some other kind of funding, but it wasn't possible in a year or 2 years. Okay, so these are the tranches that we split up into. So the study's been running since April 2020. So we have regions, the periods of time with varying levels of prevalence, whether schools were open or shut, what variants were present, and so on. And then we keep adding tranches, and the plan is to release updates now that the methods have been peer reviewed, is just to release short updates, for tranches 7 and 8 and 9 and other ones on a more ad hoc basis, rather than keep trying to write academic papers. So the point of the split into tranches is to leave the variables of interest well approximated as fixed during the time period in questions. That's are you swab positive at any point in that time, household size, because households do change. People have babies and people leave home and all sorts of other things. But those tranches are sort of short enough that constancy is a reasonable approximation. There's the alpha and delta variant. In all of this, we're identifying virus gene target failure and time, not genomic sequencing. That's another work to come. Age of participant, work in patient-facing roles, and so on. so for the different tranches, the first thing you'll notice, of course, is this is huge data. So before the pandemic, you know, a big household study would be a few hundred like Tecumseh, right? And now we've got, you know, hundreds of thousands of households. And so it's a kind of embarrassment of riches almost working out how we're going to make that work. So these are just some statistics for the numbers of how the quantities of interest break down. This is just because, you know, I won't go through every bit of notation, but a household just means a partition of the finite population into unique overlapping finite sized groups of individuals, right? And so here's before jumping into the modeling, we should do some exploratory data analysis. I'd be a terrible hypocrite if I didn't as well, because I'm always yammering on it. Students about how to do it. So just to give an idea of where the information is in these data, if we look at the count of households with a certain number of positives for each tranche, yeah. Of course, these are dominated by households with no infections, because even high prevalence is like 1% for this pandemic. But conditioned on 1, what you see is that 2 and 3 and more are very much more likely than would be expected from taking 1 squared, right? And that is because of transmission. Transmission generates an over-dispersal in these distributions compared to the binomial or Poisson distributions. In some cases, that's extreme enough to give a U shape to the attack rate. Okay, so you can see this sort of U shape, but certainly, you know, the fact that 3 and, you know, these don't go like a power, right? As you'd expect for the Poisson, the distribution is much higher variance. And so that's where the information on transmissibility comes from. Okay, the other thing we can do is do a sort of 2D histogram. And this was before we had time to kind of fit, or while the models were still chugging and trying to fit on the ONS system. This showed that because there were an appreciable number of households with only positives in children. So these are number of observations by each tranche with, you know, and you see this bimodalism is even stronger here, right? That it's not like this is a unimodal distribution. You tend to get density on the edges and in the middle here, right? The proportion of the household. These are the households that had some fraction of child and adult positives. Some households only have the child positives, right? And so that what this sort of showed early on was that unfortunately there is a role of children in transmission, right? But it's sort of intermediate. It's not everything like it would be for flu or RSV, and it's not nothing, right? And so then I came up also with this kind of fast analysis that didn't need a kind of explicit fitting step, and so was more robust, based on Pearson residuals, which are things that measure the deviance from the deviance of a given contingency, you know, a given thing that you tabulate. They measure how far that is from independence, right? So how correlated things are. And what you see here is these are kind of just raw counts of pairs, and you see this kind of clustering here of wild type. Then you see a sort of clustering of the S gene target failure associated with the alpha variant. And then we start to see delta coming back in tranche 6, S positivity coming back in with delta in tranche 6. And like I say, tranches 7 and 8 and 9 are kind of in the pipes where we will, you know, you can guess what we'll see. But what these plots do is show that they show the extent to which these things are sort of more correlated than you would expect from their overall prevalence, right? And that excess correlation tells you something about how they're driven by transmission, right? Then fitting the mechanistic model, right? So the Ball equations are based on the Selke construction, which is everyone picks an exponential random variable, and that's depleted. You do a lot of fiddling, and it turns out that you can get a vector of probabilities of all the different household final sizes out from solving a simple, a computationally simple, although the mathematical expressions are fiddly. You can just tell your computer to solve a linear system of equations, which is quite quick on a computer. Okay, and what this does is it sums over all the different transmission routes. So if we go back quickly to this, what that maths does is solves over all the different red trees that are consistent with the patterns of positivity observed over a time period, right? So that's why you need to do the complex maths. But by doing that, we then don't have to impute it in MCMC. So we're much less computational effort involved in solving a set of linear equations. And that meant this was kind of doable on huge data in short times on limited compute. And the different components are, there's a risk of infection from outside. And our sort of innovation is to add covariates to this. Our kind of methodological innovation is to add covariates to this. Then there are these equations for transmission within the household. This kind of interesting thing saying how variable is infectiousness pops up for this kind of technical reason, but I think I'll kind of skip the maths and people who want to see that it's in the preprint and the paper. But again, we add covariates and a correction for the size of the households. Large household sizes reduce the per person infection, but still act as amplifiers of infection overall. And then so we fit a likelihood. The likelihood involves lots of linear solves. Actually fitting lots of linear solves is kind of non-trivial. So even though a linear solve is fast, it's a good idea to be clever with with the library that you use for the linear solve. Then we use a Laplace approximation with a sort of standard prior, just as a way of regularizing the problem. So because it's a kind of complex nonlinear model, the likelihood surfaces can end up a bit choppy and with sort of false local maxima. So we regularize that a bit with a standard prior. Okay, which so the prior slightly reduces sensitivity to real effects, but it controls false positive discovery, right? And then these are the point estimates, right? But more importantly, they're just tabulated. But this is the baseline probability of external infection, which goes up and down basically with general prevalence, except in tranche 6, which is the first point where we see vaccination really biting. So even though prevalence was huge, that the rates of coming into the household were sort of less, and because vaccine and the rates of transmission were less, right, within the household. And so we don't explicitly model vaccination at the individual level here, but we see from over time, baseline transmission goes down because of vaccination, right? And our ongoing work is involved in doing vaccination at the individual level. And then most sort of interestingly, we see this strong effect of alpha being initially S failure being associated with lower transmissibility. Then during the alpha sweep, S failure is associated with higher transmissibility. Then during the delta sweep, it's again associated with lower transmissibility, right? So S gene target failure comes through as this is within household transmissibility, comes through as a really strong effect. No big effect from age until it becomes the case that children are not vaccinated and therefore end up being more susceptible. Working in a patient-facing role is associated with a lot more external infection until all the healthcare workers are vaccinated. The external force of infection from children is higher when they're at school. And so again, this is sort of not terribly surprising. It isn't the result we wanted. I think we all hoped the schools were going to end up to be kind of less involved in transmission than they are, but they aren't. At the end, it's sort of settled on this intermediate level of transmissibility in schools. So thanks to the CIS team, JUNIPER and all these other people.
Great, thank you, Thomas. Does anyone have quick questions? Because I know Thomas has to leave to get to another meeting. And if not, then if people have questions, they can always post it in the chat, and I can always ask Thomas and follow up with them later, because I don't want to make you late for your next.
So no, I'm here for another 5 minutes, of course.
Okay, yeah. Okay. Yeah. I guess one question I then have, which you sort of just mentioned about the genomics, and so I guess it's more on sort of future plans. So what are your plans for incorporating sort of sequencing data into this, and are you working with like Katrina Lithgow and things on? Yeah,
so we're trying to do a really fancy analysis, but of course, as people imagine with Omicron, we keep getting pulled back into doing like immediate ones, but the thing we're of course working on is a model that includes vaccination, is a bit more clever about how we call the strains using the genomic, so roughly that model, but without the individual level, when people have been vaccinated, when they've been previously infected, and actually calling it for Alpha and Delta as much as we can, not just looking at S target failure.
Cool, thanks, Thomas. So does anyone else have any questions for Thomas? If not, then thank you very much. It was a really great talk, very interesting, and